Welcome to your IELTS listening practice from Spinta.org. This is a mini-test designed to help you practice a specific section of the exam and improve your confidence. The recording will be played one time only, just like in the official test. Let's begin.
Welcome to our exploration of addiction neuroscience, the study of how addictive substances and behaviors alter brain structure and function. Modern neuroscience has revolutionized our understanding of addiction, revealing it as a complex brain disorder rather than simply a failure of willpower or moral character. This scientific perspective has profound implications for treatment approaches, policy decisions, and societal attitudes toward addiction. The brain's reward system lies at the heart of addiction vulnerability. The mesolimbic dopamine pathway, connecting the ventral tegmental area to the nucleus accumbens, evolved to reinforce survival behaviors like eating and reproduction. Addictive substances hijack this system, triggering massive dopamine releases that far exceed natural rewards, creating powerful associations between drug use and pleasure. Chronic substance use leads to neuroadaptation, compensatory changes that maintain brain function despite ongoing drug exposure. The brain reduces natural dopamine production and receptor sensitivity, requiring increasingly larger doses to achieve the same effect. This tolerance develops alongside physical dependence, where normal brain function becomes contingent on continued drug presence. The prefrontal cortex plays a crucial role in addiction development and recovery. This brain region, responsible for executive functions like decision-making, impulse control, and planning, shows reduced activity in addicted individuals. Weakened prefrontal control makes it difficult to resist cravings and make rational choices about drug use, perpetuating the cycle of addiction despite negative consequences. Genetic factors account for approximately 50% of addiction vulnerability, with specific genes affecting drug metabolism, neurotransmitter function, and stress response. The COMT gene influences dopamine breakdown, while variations in the mu-opioid receptor affect pain sensitivity and euphoric responses to opioids. However, genetic predisposition does not guarantee addiction development, as environmental factors significantly influence outcomes. Stress and trauma profoundly impact addiction risk through effects on the hypothalamic pituitary adrenal axis. Chronic stress increases cortisol production, which sensitizes the brain's reward system to addictive substances. Childhood trauma particularly elevates addiction vulnerability by disrupting normal brain development and creating lasting changes in stress response systems. Different substances produce distinct neurobiological effects while sharing common addiction pathways. Opioids bind directly to mu-opioid receptors, producing euphoria and respiratory depression. Stimulants like cocaine block dopamine reuptake, creating intense but short-lived highs. Alcohol affects multiple neurotransmitter systems, including GABA and glutamate, leading to complex withdrawal syndromes. Behavioral addictions involving gambling, gaming, or social media activate similar brain circuits as substance addictions. Neuroimaging studies show comparable changes in reward processing and impulse control regions, suggesting shared underlying mechanisms. This finding has expanded addiction models beyond chemical substances to include behaviors that trigger compulsive engagement despite negative consequences. Treatment approaches increasingly target specific neurobiological mechanisms of addiction. Medication-assisted treatments like methadone and buprenorphine normalize brain chemistry while reducing cravings and withdrawal symptoms. Cognitive behavioral therapy helps rebuild prefrontal cortex function through skills training and habit modification, while mindfulness-based interventions strengthen attention regulation and emotional control. Future addiction treatments may leverage emerging technologies like transcranial magnetic stimulation to directly modulate brain activity in addiction-related regions. Pharmacogenomic approaches could personalize medications based on individual genetic profiles, while digital therapeutics provide accessible, scalable interventions. Understanding addiction as a brain disorder offers hope for more effective treatments and reduced stigma, ultimately improving outcomes for millions of people affected by this complex condition.
You have now completed the practice test. When you are ready for a full exam experience, visit us at Spinta.org. There you will find complete mock tests for all 4 skills: listening, reading, writing, and speaking. Our platform provides instant AI feedback for your speaking and writing tasks, along with an accurate prediction of your band score. Take control of your preparation at Spinta.org.